Provisioning a single virtual machine is straightforward. Engineering a resilient, enterprise-grade compute fleet that handles millions of requests without failure requires a strict architectural blueprint. Without precise operational and runtime management, an infrastructure is exposed to runaway billing, system-halting HTTP 503 API throttling errors, and server boundary security exploits. To prevent these failures, we must master 4 specific domains: financial provisioning models, local metadata boundary security, ingress network routing, and local OS telemetry limits. Integrating these interconnected layers is the required threshold for keeping an auto-scaled compute fleet operational under enterprise loads. Managing a massive EC2 environment starts with commercial strategy. AWS provides 8 distinct purchasing pathways to match specific workload profiles to the correct cost and tenancy model. The baseline is on demand. You pay strictly for what you use, billed per second of execution for Linux and Windows instances. This carries the highest unit cost but requires 0 long-term commitment. For predictable workloads, reserved instances and savings plans require 1 to 3 year commitments in exchange for discounts of up to 72%. Spot instances leverage unused AWS compute capacity to offer up to a 90% discount. This model requires a workload capable of handling a 2-minute AWS termination notice if the spot market price rises. Hardware isolation requires specific models. Dedicated hosts give you bare metal visibility into physical sockets and cores for software license compliance, while dedicated instances provide isolated hardware without direct control over instance placement. Finally, capacity reservations lock in physical space within a specific availability zone. You are billed at standard on-demand rates, whether the instance is actively running or sitting idle. This comparative data table reveals the exact per-hour pricing for an M4, large instance deployed in the U.S. East 1 region, allowing us to measure the financial impact of these architectural commitments. The baseline on-demand price is exactly 10 cents per hour. Migrating that exact same workload to a spot instance drops the fluctuating cost to under 4 cents per hour, a 61% discount. Locking in a 3-year, all-upfront reserved instance drops that cost further, hitting an optimal 3.7 cents per hour. Your commercial selection dictates your physical constraints. Precise financial engineering defines the scaling capacity a team can afford to deploy. Once provisioned, instances must discover information about themselves. They do this via the internal EC2 instance metadata service at the link local IP address 169.254.254.254. This service allows an instance to learn its own IPs and retrieve temporary IAM role credentials, though it can never expose the underlying IAM policy document itself. The legacy IMDSv2 protocol relies on direct, unauthenticated requests. An application's operating system simply makes a plain-text HTTP GET request to the link local IP to retrieve data. This presents a vulnerability. If an attacker exploits a server-side request forgery, or SSRF, in your application, they can use this plain-text GET request to steal your temporary IAM credentials. To mitigate this risk, you must enforce IMDSv2. This replaces plain-text queries with a mandatory 2-step token validation process. In Step 1, the instance executes a local HTTP PUT request containing a time-to-live, or TTL, header. This generates a temporary session token valid for up to 6 hours. In Step 2, the application must append this precise token into the HTTP header of all subsequent metadata requests. If the token is missing, the IMDSv2 engine rejects the call. Enforcing the IMDSv2 architecture neutralizes SSRF threats at the host level, ensuring that instance-level credentials remain inaccessible to external request forgery. Managing this fleet programmatically introduces hard constraints. For example, AWS throttles the Describe Instances API at 100 calls per second. Exceeding this rate returns an HTTP 503 error. To maintain control, scripts must implement exponential backoff algorithms. This restructures request timing into paced intervals to handle intermittent 503 errors. With management scripts paced, user traffic must be routed effectively. AWS provides 3 distinct elastic load balancing topologies. The Classic Load Balancer, or CLB, is a legacy version 1 architecture. It operates across Layer 4 and Layer 7 using a fixed hostname for routing. The Network Load Balancer, or NLB, is a high-performance Layer 4 TCP and UDP router. It is engineered for extreme throughput and allocates exactly one static IP address per availability zone. The Gateway Load Balancer, or GWLB, operates at Layer 3. It is designed specifically to route all VPC traffic strictly through fleets of third-party virtual security appliances. Regardless of the router, scaling requires safely terminating instances that are actively processing user traffic. You configure connection draining on classic load balancers, or deregistration delay on network and application load balancers. When an instance begins deregistering, this mechanism immediately halts the routing of any new requests to that specific node. Simultaneously, it keeps active connections open for a configurable threshold, defaulting to 300 seconds, to allow existing transactions to finish processing before the instance goes offline. Precise connection draining ensures that auto-scaling events and fleet updates occur with zero visible downtime for the end user. Those auto-scaling events are executed by an auto-scaling group, or ASG, which dynamically adjusts fleet capacity based on live system demand. The structural blueprint for the ASG is the launch template. It defines exactly what to deploy, including the Amazon machine image, instance type, EBS storage bounds, and IAM roles. Scaling decisions rely on standard CloudWatch telemetry. By default, EC2 instances push metrics every 5 minutes, or every 1 minute if you enable detailed monitoring. This chart and metric view reveals a critical blind spot. AWS hypervisors have zero native visibility into the internal operating system states of your instances, meaning they cannot see your active memory usage. To scale based on memory utilization, you must install a local agent inside the operating system to extract that telemetry. This agent utilizes the PutMetricData API to push custom metrics directly to CloudWatch at high-resolution intervals, ranging from 1 to 30 seconds. This custom data feed allows the ASG logic to trigger the automated launch of new capacity the moment memory becomes bottlenecked. Bypassing default hypervisor limits via local OS telemetry is the only reliable way to effectively scale memory-bound applications. Returning to the complete end-to-end architecture, we can now trace how these advanced mechanisms interconnect. We see the financial tags on the back-end instances, the IMDSv2 token lock securing local metadata, the NLB draining active packets, and the custom RAM gauge triggering a back-end scale-out. Standardizing on these configurations requires matching workload profiles to purchasing models, enforcing metadata TTL tokens, configuring Layer 4 and 7 connection draining, and bridging hypervisor gaps with custom telemetry. These integrated operational layers enable a compute fleet to maintain high availability and cost efficiency under production scale loads.